This is it. We've made it our last new lesson of the year. After this, we're going to start some review, but we're at day 96. So, day 96 is just going to build on day 95, where day 95 we used solid, what we call discs, thinking of like frisbees or a small cake or something like that, and stacked them all on top of each other and it made a three-dimensional shape. So our warm-up today to build on that is going to introduce us to the idea of an annulus. An annulus, or sometimes called a donut or anything like that, is when you have two concentric circles, concentric meaning one inside the other, and you're asked to find the area between those two circles. So it's going to be this area right there. See that donut? So you're asked to find the area of that outer ring, or the ring in between your two circles. They give you these two right here, and then they say after you find that, awesome, if you could please create a generic formula if we didn't know the values of lowercase r and uppercase r, that would be swell. So pause the video, take a minute, figure out the two areas, or the two formulas rather, and then unpause the video. Alright, so we're back. Let's see how we did. Hopefully you treated this as really two separate problems. You said, well, we've got this really big circle right here and this radius of r, which is going to equal 5, and then we have this smaller circle that used to be here, but I'm just going to draw it separately, and this smaller circle has another radius, which in this case we're going to call 3. And to do it, we're going to find the area of the big circle first, and then subtract the area of the small circle, of course, because the big circle is going to be all of this, but if we're able to take out this smaller region, then it's just going to leave us with the region around the outside. So as we go through, if we want to find the area of, and I'm just going to do area sub big R, or capital R, it's just going to be pi times our radius squared, 25 pi. And then we can do the same thing with our smaller circle, and that's going to be pi times 3 squared, which is 9 pi. To find the overall area of the annulus, we're just going to take that 25 pi, subtract 9 pi, and hopefully end up with 16 pi. Nothing terrible. Now if you wanted to do this generically, I'm just going to skip right to this step right here, but I'll keep the same colors. We would do pi times our big R squared minus, and then we have pi times our little r squared. And that is the formula of the area of an annulus, right? So our area formula is right here. Now, thinking of combining like terms, it seems like there's at least something in common to both of these. I definitely see a pi that we could factor out, and that would leave me with big R squared minus little r squared. What about the square? Could we make things a little bit easier, and we could say that this is capital R minus little r, that quantity squared? Well, hopefully that's setting off some alarm bells for you, and you're saying, whoa, 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 we can't do that, because we know we can't distribute or undistribute a power if we have addition or subtraction on the inside. So this is a no-no. You are welcome to clean up the formula if you want. You're welcome to keep it separate if you'd like, totally up to you, but don't simplify too far. That's all this note down here is telling you. Alright, we only have one sample problem today, so we're actually this is going to be a pretty long video. I'm going to take you through the rest of the problems, but as before, after we finish this example problem, you should try the rest of these with the video on pause, and then come back if you need help. But here we go. Find the volume of the shape created by an area bounded by blah 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 and blah 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 is rotated about the x-axis. Okay, well, first thing is I'm going to graph this. We're rotating around the x-axis, which means I'll probably need a positive y and a negative y section. I'm not sure how much space I'll need yet. I'm also going to need each of these, and they're going to cross probably somewhere. How do I figure out where they cross? I bet you could eyeball it, but let's do a little bit of algebra. So if I want to see where these two equations intersect, the nice part is they're both equal to y, which means we can substitute one into the other, and that's going to give me x is equal to the square root of x. That's kind of a weird equation. I don't like the square root, so let's square both sides. X squared equals x. Pull everything to one side. X squared minus x equals 0. And then remember, to solve something with two different x's to two different powers, we factor to here, and we make two equations, which hopefully we can see the answers will be 0 and 1. So So that tells me they're going to cross at the points 0 and 1. 0 what and 1 what? Well, just plug your x values into either one of these original equations, and I think you'll see it's 0, 0, and 1, 1. Very inventive, very exciting. So we have the point, and I'm going to scale this probably pretty poorly. Let's call this one. Let's call this one over here. Here is 1, 1. Here is 0, 0. We know that our graph of y equals x is just a line. Maybe I'll do this one in, how am I going to do this? We'll do this one in kind of purplish. That's going to look, hopefully better than that. It's going to look something, nope, second try, third try. That's decent. Okay, there is my line y equals x. And then we have to graph the square root of x, which I'll do in a pleasing yellow. We know the square root of x is concave down everywhere, and yeah, I think that's fine. Okay, so now realize that the area bounded is this area on the inside. It does not include this area down here. So it's just this floating region that kind of looks like a leaf. And what we need to do is, again, rotate it, having trouble erasing, rotate this around the x-axis. So the first thing I'll do is the same I've done before. I'm just going to go ahead and extend this down a little bit further. It looks like 1 would be right about here, same space, -1 I guess, and then I'm going to do the same thing. So I've got this down here, and then I have that same curvature like that. That's looking pretty good. Kind of looks like one of those Mario flowers that spits fire at you, but either way. Okay, so we end up with this. Now, what's going to happen here is, as we've done before, we are going to see some circles get drawn. This purple one I'm going to do first is going to have some circles that look like this. All right, nothing too terrible. Maybe I'll solidify that one. Sure, something like that. Okay, but then the weird part is this part on the inside here, this is open. There's nothing solid here. The solid section is up here. So what I really need to do is rotate the outer one as well. And I like to take corresponding points with the first circle just to see this. And then here's my next corresponding point. Looks something like that. And then my last corresponding point there in the same spot. So I kind of just shade in next to it. Something like that. Now, picturing what this looks like is a little bit challenging. And once we meet as a class, I'll try to show it to you. But really what's happening is this inner piece that's right here is completely hollow. If you looked at this shape, this would be open on the inside. You'd be able to stick your head up through it. In fact, on the inside of this, you can see that the walls, are pretty smooth and flat. You can think of the walls as like an ice cream cone. But then the weird part about it is once you burrow through the wall of the ice cream cone, there's a second solid layer. So it's going to make the outside of this kind of look like a coconut. So maybe you can picture like a coconut, but then on the inside there's scraped pointy thin. So it's like a coconut with an ice cream cone put inside. And so what we're interested in is that wall boundary in between my cone and my coconut shape. So how do we do that? Well, the first step is probably to redraw this in a way that makes a little bit more sense. So I'm going to keep my same colors and realize that we're going to be working with a circle in yellow and a circle in blue. Now the very inner part of this blue circle is the open space, right? That's maybe if I redo this one, that's that open space right there. The section we're interested in though is this red part on the outside. And now it should be making a little bit more sense as to why we warmed up finding the area of an annulus. Because we are going to be finding the volume by stacking multiple annuli. I assume that's the plural, annuluses? I don't know. These multiple annuluses, annuli I think sounds better, on top of each other. Now, most people don't say annulus. Instead, they call this a washer, right? And you've seen washers hopefully before. You have, screws, you put a washer on as a buffer when you're screwing something in, right? So either way, you could also call it a ring. Sometimes this is called the ring method, a washer or a ring, that has that solid piece right here and the open piece on the inside. And what we're going to do is the exact same 3 steps we've done before. So first step, I'm going to need to find the area function for my annulus. And I know the area is going to be pi times big R squared, yeah, I should probably write this way, pi times the big R squared minus pi times the little r squared. That's how we find the area of the ring. And extending a little bit further out, we're going to need to see what is big R and what is little r. Well, big R is going to be the largest radius, right? That's why it's going first. And my largest radius you can really draw again from anywhere on here. I could draw from this point down to the middle if I wanted. I could draw from here up to the middle, but I want to make sure that the two endpoints start and end at functions I actually know the equation for. The middle is really easy. That's just going to be 0. But down here, I don't know the equation for this function, so I'm probably not going to draw my radius that way. Instead, I am going to draw from the top down. So from the top down. I'm going to call this big R. And big R in this case is going to be the top function, which was our square root of x, minus the bottom function, which is just the easy function 0. And again, put both of those in there to start. Think of this always as top minus bottom or right minus left depending on the direction we're going. And then I'll do the same thing for the second one. So I'm going to go ahead and I'm going to do, and this one's a little bit harder, so I'll just use a different one over here, right? I'm going to offset this so we can see what's happened. Little r, right? And little r is going to be drawn from the what am I thinking? Oh, this line, the linear function. That's it. Okay. Wakey brain. So the top function is the linear function, and the bottom function is again 0. Okay, well, we've done that. That's awesome. There's our area function. Now, what else can we do? Well, we need to give it volume if we want to find the volume of a three-dimensional shape. Volume is going to be the same as before. I'm just going to go ahead and give this ring a little bit of a third dimension here. You'll notice the third dimension is going across the x-axis. That's going to be this dx right here, right? We're stacking a whole bunch of rings or washers on top of each other this time. So my third dimension gives me my volume formula, and I'm going to simplify this a little bit. It's going to be pi times square root of x squared minus pi times x squared. That's the area. To give volume, we need a third dimension, and there's my dx. Alright, well then we need to actually find the integral of all this, because this will just find us one of these washers. We need all of them. So we're going to go ahead and integrate. To again make our life a little bit easier, let's simplify one more time. We're going to go pi times x, right, square root and square, minus pi times x squared dx from where to where? Well, I think we start with our rings at 0, an x of 0, and we end with our rings at an x of 1. I think we're looking okay. Let's finish this off. Realize that there's pi in common to both, so I'm going to factor out the pi out front before I do my antiderivatives. X minus x squared dx. Okay, continuing off. Antiderivative time. 1/2 x squared minus 1/3 x cubed. Looks okay from 0 to 1. And then, of course, we do have to plug in 1 here. So we get pi. If we plug in 1, we're going to get 1/2 minus 1/3. If we plug in 0, we just get 0. So that's easy. And hopefully we know that 1/2 minus 1/3, when you give them common denominators, is 3/6 minus 2/6, which is 1/6. 1/6 times pi gives us our answer of pi over 6. So at this point, you really have all the knowledge to do any problem on the AP exam, and I'm pretty proud of you for that. You have one last practice on this assignment. It's 3 more pages, and I'll take a look at this just so I can remind you of what you need to do. You're going to be given a problem, and sometimes you'll be given a graph, other times you'll need to sketch in a graph. I've also tried to leave you space on the graph so that you can sketch the 3-dimensional reflection part. And then there's work for the volume down here, or space for the work. And then the last question is, what are the tricks or maybe a pitfall that someone might fall down into if they're working through this problem? Because each of these is going to be a little different from each other. And it's your goal to figure out A, how to do it, and B, what might someone struggle with. So you should pause the video now, and there are going to be 1, 2, 3, 4, 5, 6 problems for you to try. Go ahead and try all those, and then when you're done, come on back. All right, so I'm going to go ahead and go through each of these. Again, a bit of a long video today, but you don't have to go through all of them. Just skim to the end, see if you were right. If you weren't, then go back through. So we have this piece right here with my region R. We're rotating it about the horizontal line y equals 2. So here's my line y equals 2. So the first thing I always like to do is to reflect this region. It's at 0, 0, so let's see, up 2, so I need to go up 2 more to 4 to get this piece, right? There's that straight line piece, and then there's a curvy piece on the inside, so that's going to be something like that. All right, that's pretty good there. Then we need to revolve the region around this line. So I'm going to do 2 sets of colored circles. We have, and I'll do a small set, medium set right here. Here's my first set. All right, and I'm going to do them in blue. And then here's my second set, and I'll do them in orange. No, I already used orange. We'll do them in red. It's going to look like this, and it's going to be the outer function. All right, the outer function and the inner function are in the same spot here. And then we could do one more here. Why not? There's that. And here is the tiny one like so. All right, this is another ring or washer problem. So let's break apart that washer really quickly. And I'll maybe do it over here. So we've got the red function, and I'll just do them in 2 different spots. I'm going to have my big R up here and my little r down here. So we have to figure out the radius again. You might be tempted to start your radius for the big circle from the top function down, but remember, we don't know the equation of the top function, so I'm going to go ahead and do it from the bottom function over here. So this is going to be my big R. How do we find big R? Well, remember, no matter how we drew the radius, it's always the top function minus the bottom. The top function here is 2, and the bottom function is going to be that y equals x divided by 2, right? 1/2 x up 1 over 2, but I'll leave it as x over 2 for now. All right, what about the blue function? Well, the blue function is going to be pretty much the same. It's just going to be here to here this time, right? And I'm going to call this little r. And to find my little radius, top minus bottom. The top function is 2. The bottom function, the curvy one, is that square root of x. And honestly, we're probably ready for our volume. So to find the volume here, we're going to sum up all of these, and it's going to be pi times big R, 2 minus x over 2 squared. That's going to be too much, so we need to subtract off pi times little r, 2 minus the square root of x squared dx. And then, oh, well, the and then is, what are my limits of integration? Well, it looks like we're starting at 0, we're ending at 4, and we're set. So, tricks or pitfalls, that's a really personal choice. I think, having graded a billion of these over the last few years, that the major thing I see students do wrong is they forget about this function here. All right, they forget about the concept of top minus bottom, and instead they just think the outside function and the inside function. So a lot of their integrals will be set up with just the outside function squared minus the inside function squared. That's not what we're doing here. We need a radius that's drawn from the top function to the bottom. So ultimately up to you. It could be something else. I'm excited to see your answers there. Okay, second one. What are we doing here? Integral to find a volume revolved around the line y equals 1. Okay, so it's pretty much the same thing, I think. Here's y, oops, that wasn't great. Here is y equals 1. Go straight across like so. All right, and then we're going to do the same thing again. Started at 0, 0, went up to 1, so I think this one needs to be, spacing-wise, goes up pretty far. Something like that. Let's see, it curled up here, so it's got to curl down there. And then this one went up, so this one's got to go, oof, got to be a little bigger here. Got to curve out that way. That one's pretty good. All right. And then we rotate. Okay, same thing, circles again. I'll only draw one set this time. We're going to have one circle that's here, and we're going to have a second circle that's here. This one's a lot harder to picture because it's kind of smushed, but it's looking okay so far. And then we can break apart each of these. This is going to be mine for big R. This is mine for little r. Big R, let's see, which function? We know the bottom function, so I think this is going to be my big R right here. and it's got to be top minus bottom again. Top function is 1. Bottom function, what is the bottom function? Huh. Well, they told us 1 is 8x cubed and 1 is sine of pi x. This really comes down to, do you know the shape of your graphs? And hopefully you know that an x cubed graph looks like this, and the sine graph always starts at 0, 0, and goes like this. So I'm pretty sure this bottom function right here is going to be 8x cubed. So 1 minus 8x cubed. Okay? And then, of course, we need our little r. Little r is going to be kind of right in here this time, overlapping, and that's got to be 1 minus sine of pi x. And then we put it all together. So our volume integral pi times big R squared. Can drop those parentheses once you're sure you've distributed your negative, minus, and then we need pi times little r squared dx. Awesome. And we need to sum up from my first x value to my second, 0 to 1/2. Tricks or pitfalls, very similar to the first one. I've seen people screw up identifying which function is which here, but other than that, very, very similar. So let's go ahead and move on. All right, let R be the region in the first quadrant with those two functions. Set up but do not solve an integral to find the volume of the solid when it's rotated about the vertical line, x equals -1. Ooh, we got a lot going on here. So I'm going to go ahead and draw something. Let's see, let's center this here. And not even center it, we should probably shift it. Ooh, I don't know, this could be a tricky one. Yeah, we should probably shift it like this though. So here's this, here's that. Let's get everything involved. Let's start with x equals -1. Here's -1, -2, -3. Here's 1, 2, 3. I might have made this too squishy, but that's okay. Or I could have done it terribly wrong. So let's do a little bit of work here. We have the square root of x. We know what that function looks like. It crosses at 1, 1, and all sorts of other things. But we don't know where these two cross, and that will be important at some point. So I'll just use the little space up top. We're going to have to set the square root of x equal to x over 3. I think we'll probably have to square everything. So x will equal x squared over 9. Multiply by 9, 9x equals x squared. Subtract, and I'm going to switch the sides, so x squared minus 9x equals 0, which tells us these x's are going to be, I should have done this first before I drew my graph, are going to be at 0 and 9. Alright, well, what are the y's that go with that? We have the point 0, we plug it into either, we get 0, and we have the y value 9, square root of 9 is 3. So our x-axis actually needs to go up pretty darn far, so I'm going to redo this. Actually, don't need to do too much, I just need to change my scale of my x-axis, I think. There we go. Okay, let's try this again. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Add 2 more for good luck. Okay, here we go. Trying again. So we have the graph of y equals the square root of x, and we can plot a couple points. No, let's go. Let's elongate this. Since we only have to go up to a y of 3, let's make it look weird. 1, 1, right? If we plug in what else is going to give us a nice answer? Square root of 4 is going to give us a nice answer, and square root of 9 is going to give us that other nice answer. So here is my square root function, and then we also need x over 3, and I imagine that it's going to be underneath something like this. So here is my square root of 3 graph. Okay, now what do I need to do with this? Well, I need to go ahead, take this graph, and revolve it around the line x equals -1. X equals -1 is this line right here. So this is different. Now instead of spinning it vertically, we're spinning horizontally. And I will tell you one thing that most people miss on this is they forget that there is a gap right here. This gap kills people. So if this is one step away from the line, then when I redraw this shape, there still needs to be that same gap on the other side, right? That's here, and then we went up 1, over 1 from there, and this doesn't have to be exact, and then you can keep it going. So what you could do is you could draw the actual points that we did before, and then shift them all 2 to the left, whatever sounds good to you. I'm just going to make it up. It doesn't matter that much. but I still want it to be curvy. So let's do something like this. There we go. There's that one, and there is that one. Decent, a little bit longer on the left side, but we'll survive. Okay, so we've got my mirror image now. Then we need our circles. So circle-wise, now we're going to be going this way. I'll just do 2 of these here. Okay, there's my inner circle. That's going to be my smaller one. And then we, of course, need our outer circle. I can do one more. I always say that, and then it never goes well, but that's okay. All right, let's do the outer circle. So we've got this one corresponding points over here. It's going to go down and not run out of room. There we go. And then same thing down here. It's going to go down, go around. Okay, so this again is a shape that is going to be hollow through the middle. All this stuff in the middle is hollow. And it's really going to be the opposite of the first graph we started with. This one is kind of going to look like a cone, but the bottom's cut off. It's open at the bottom as well. And on the inside, it's like an inverted coconut. It's like a, oh, I don't know, maybe a good way to think about it. It's kind of like when you walk into those museums and you take a coin and it spins around a funnel and goes down and down and down. It kind of looks like that. But either way, we can still figure this out even if we're not sure what it should look like mentally. So we have our outer circle, our bigger circle, and our smaller circle. One thing to note though, before we start finding our radii, is when we give this circle 3 dimensions, when we make it three-dimensional washer, which is three-dimensional, this itty-bitty width is along not the x-axis, but now it's along the y-axis. There's going to be a dy in our volume down here, right? Our volume is going to equal the integral of all sorts of fun stuff, dy. And that should be a giveaway from the last few days then, that all of our functions need to have y's in them, not x's. So we have a little bit more work to do. Okay, well, I can do that right here. If y equals the square root of x, then if we square both sides, that means x equals y squared. Graph either of those, they make the same shape. And if we have y equals x divided by 3 and we multiply both sides by 3, then that gives me x equals 3y. There we go. So now we have our functions in terms of y. Let's write our radii. Big radius first. Okay, my big radius, I need to go from the very center, which is this point here, and I could either draw this way, though I don't know that outer function, so that doesn't seem good, so let's draw the other way. And now because we're going side to side, we need to do our right minus left. Our right function is the linear equation, that's 3y, and my left function, the real kicker here, is the line -1. Other radius, we have lowercase r, and this one I'm just going to write right over top. It's going to be right here. Right function is the curvature one, that's my y squared, minus the left function, -1. So as we actually write our volume formula, pi times big R squared, don't forget to distribute the negative, so it becomes +1 squared, minus, that's a circle, we need to subtract the smaller circle, pi times y squared plus 1 squared. And we're just about done, but then we need to add up or stack up all of these washers. They need to be in terms of y. You can write y equals so you don't forget. 0 is the smallest. The tallest y value that we get up to is this one right here. You'll notice it's in our 0.2, and that's all the way up to 3. There are many tricks in Pitfalls. You might want to list a couple here, or you can write down the ones that you thought were the trickiest, and then move on. Alright, right but do not solve an integral, rotating region lies in the first quadrant about the y-axis. Now about is really just a fancy way to say around the y-axis. So let's get our graph rolling. Now, this cube root of x, I'll probably draw this twice, but the cube root of x looks like this, right? The square root just sits in this quadrant because you can't do the square root of a negative and get a real answer, but the cube root you can do negative, so it looks like this. X over 4 is going to look something like that. Now, well, actually it should go all the way through, huh? So it tells us though that we're only going to take the region in the first quadrant, so I don't care about this part. We just care about that. Of course, then we're going to revolve it about the y-axis. Here's my y-axis, which means this graph is going to spin that away. Okay, and then once it spins around, we're going to need to know everything else going on. I'll also probably want to know where these two intersect each other. Maybe I'll use the space down below. Okay, so let's take a look. Where is the cube root of x going to intersect x over 4? Well, we should probably cube both sides. X is going to equal x cubed over, 4 cubed is 64, isn't it? This one's kind of gross. Who made this problem? And then multiply by 64. Okay, and then continuing on, we're going to go ahead and get x cubed minus 64x equals 0. Don't forget that I'm going to jump down because I'm running out of room here. I'm going to factor out an x, so we get x squared minus 64 equals 0. And then difference of squares, x minus 8 times x plus 8 equals 0, which tells us that x will equal positive negative 8 and 0. Okay, and when we plug 8 into our equations, the cube root of 8 is 2, so I get the points 0, 0, and we only need positive 8, comma 2. All right, but then we will need negative 8, comma 2 for the reflection. So here is our graph. We've got something like this. We know the x-axis needs to go to 8, the y-axis only needs to go to 2, so let's start with that. 1, 2, ha, winning. 1, 2, 3, 4, 5, 6, 7, 8. Cool. 1, 2, 3, 4, 5, 6, 7, 8. All right. Now let's get our initial shape. Our initial shape is going to go from 0, 0 to 8, comma 2. We can just curve it. Doesn't have to be perfect. And we're, of course, going to have our line as well. Something like that. Cool. And then when we reflect it, it's going to have our negative 8, comma 2, and it's going to have that curvature along the inside, and our straight line coming down. There we go. That's pretty good. Okay, circles. I always draw the circles. You guys don't have to, but I just think it really helps for that visual of what's the bigger circle, smaller circle. You think outer function, inner function, whatever sounds nice to you. But here is, and I'll just draw one this time. Here is my circle, something like that. And here is the outer circle. Okay, it's a very, very similar shape to our last one, but the last one had a washer that was centered around -1, made it tricky. This one's just around 0. Okay. Well, notice down here though, when we give this width again, it shouldn't surprise you, this width is going to be dy, which means our volume needs to be in terms of y all the way through. It's going to end in dy. Our y values are going to start at 0, end at 2, where we've got y values here. And so when we do our pi something squared minus pi something squared, everything better have y's. All right, well, here we go then. Outer function, inner function, big R, it's got to be this distance here, and little r has got to be this distance here. So big R, maybe I should leave some space up above. That's talking about our straight line function, our linear, diagonal linear function, which was originally y equals x divided by 4, but when we multiply by 4, we get x equals 4y. Okay, so that means then that my radius is going to be outer function, 4y, minus the inner function, which is all the way here in the middle. That's just 0. That's really nice. Really, so this is just 4y. Cool. And then we have our little r. Little r, originally y was equal to the cube root of x. If we cube both sides though, we get x equals y cubed. And so we end up with our little r, lowercase r, right here. We have our y cubed minus 0, or just y cubed. And we're set. Okay, 2 to go, I think. Thanks for sticking through. Hopefully you've been doing everything on your own, no problem. Let's get this last 2 done. Tried to throw some real curveballs at you. So let R be this region enclosed by those. R is the base of a solid, so this is something you could walk around on right here. Very exciting. For this solid, each x, the cross section perpendicular to the x-axis has an area. Uh-oh. Right, but do not solve an integral. Now notice they didn't tell us to revolve or reflect this around anything. We don't have to flip it around the x-axis. What they're telling us is this is a base. Think of this as like a dance floor again, and there's some shape that's going to be coming up out of the dance floor that's perpendicular to the x-axis. Now this shape could be like a square. Alright, it could be a triangle, it could be a circle. It doesn't really matter though, because what they've given us is they said it's some shape, but we know the area of that shape. And that's very useful, because once we have a two-dimensional shape, whatever it is, if we know the area function, we know how to turn area into volume, right? So if I want my volume function, it's just going to be the area function, that's two-dimensional already, times, well, what do we not have? We don't have any width here. So if I give this a little bit of width, right? It looks like that. Very nice. Okay, now we've given it width, which is along the x-axis, that's dx. And then if we want an integral, well, we just need to sum up all of these cross-sections. Again, I don't know it's squares or rectangles, but they told us it's some shape. And so my final volume here then is going to be the integral from where do we start summing? 0. We end summing at 2 of sine of pi over 2x dx. And that's it. So a lot of students, and this is a good pitfall on this problem, a lot of students have trouble distinguishing between these two strategies that we've learned. We've learned how to build volume using cross sections, and we've learned how to create volume using rotations. So those are the two types of volumes we know, and you really will have to keep them straight. Last one. We've done this one before. Hopefully you recognized it from a couple days ago, but it's just a good reminder. So inside of a funnel of height of 10 inches, right, so this total height rate here is 10, is shown to the right. At any height h, the radius of the funnel is given by this. So maybe I'll call it r of h is 1/2 3 plus h squared. Okay? And write, but do not solve an integral to find the volume of the funnel. Well, this one's weird, but they did tell you cross sections. And to find cross sections, there's always 3 steps. First step is you have to write your area function. Well, the area of one cross section, what are the cross sections here? Well, they told you that. This is built by cross sections of circles. So my area is just going to be pi times the radius squared. Okay? Now the problem though is that when we give this 2 dimensions, or 3 dimensions rather, it's going to be pi r squared times a third dimension here. And the third dimension is going to take this cross section and make it, of course, 3-dimensional. But this third dimension is lying across the h-axis. It's built on the h-axis, so this is going to be dh. Which means then that my radius needs to be in terms of h, not r. So pi r squared, same thing over here, pi r squared with a dh at the end. But the nice part is I know a different way to write the radius. Instead of just using r, I can use this formula, which is in terms of h, which is super useful because it's exactly what we need. 1/2 3 plus h squared. Same thing over here, 1/2 3 plus h squared. That's going to give us the volume of any one of these cross sections. We need to stack all of them on top of each other. So my overall volume then is going to be pi times 1/2 3 plus h squared. That's pi r squared, my radius, times dh. How high do I stack them? From 0 to 10. And we're done. So thank you for all of this. Make sure that you get this done and turned in on Teams, and I'll be in touch with you about what we're doing for the next month until the AP exam. Great job.